Hi and welcome to this. This is our online version of the face-to-face class that we had for maths this week. So I've tried to put together the key items that we talked about and I'll present them here so that you can all get a picture of those topics. And I started out by trying to give a bit of an overview about what we've done on the course so far and where we're heading with it, why we've taken the structure we have with the probability and statistics bit of the module. So first of all, we started out with the idea that you can have a list of data when you do an experiment. This is likely to be the sort of thing that you generate. And as an engineer, we want to do something useful with that, and we want to use our probability and statistics knowledge to turn this into something that we can use to do prediction with in the future, to work out how strong something needs to be, how thick it needs to be, how likely it is to fail, so that we can design it the way we want it to be. And we've seen that the way that we want to plot this, a very useful way of plotting it, is as a histogram, where we have our variables and we have this thing called the relative frequency density, which is the one that I have emphasized as being useful. And we take intervals and we plot out what our distribution looks like. And so this is just some random sort of example for that. And once we get to this point already, we can start to do some useful things. We can identify the median, for example. So one of the features of this, because we've taken the relative frequency density, relative means that we divide the each quantity for each interval, we divide it by the total number of data points that we had, and then the density means we take the value for each interval and divide it by the width of the interval. And when we do that, the total area under this graph is going to be equal to 1. And that's very useful because we're generalizing this data away from the specific experiment we did. We're generalizing it to start to make it representative of the actual material properties that we were looking for. I suppose we should remember that where does this start? Well, it starts from where we have a population of data, and then when we do the experiment we just get some sample of that whole population. And what we really are interested in is the population. What's the true properties of the material that we're looking at in the materials testing example we started our lecture with? We're interested in what's the true properties of the material, that is to say, of all the infinite number of different samples there might be of it around the world. And we just have a few samples with a few measurements. That's our sample, and from that we're trying to find out what the population is doing. So first of all, we put it into the relative frequency density. That generalizes it, gives it an area of 1. So this starts to become representative of the population, not just of the sample. So if the area is equal to 1, what happens when we get to 50% of the area? So if that area there is 50%, well, that's like saying that for any sample we have, there's 50% chance of it being on this side or 50% chance of it being on this side. And so this line marks the middle of the population of data based on the number of points, and that's what we call the median. But we also know that we can characterize the data by considering the mean. The median and the mean are different, and the key difference between them is that the mean takes account of every single value of the data. The mean is a function of all of these values, whereas the median only counts them up and finds the middle one. So the median is only actually a function of the middle data point and the total number of data points, whereas the mean is a function of all the data points. So that means that if our data is, if it's symmetrical, if it's perfectly symmetrical, the median and the mean are the same. But if we get some data that's starting to drift away from the middle, like here, we've got a bit of a tail on this data, all of these data points are going to be contributing to the mean, but they're not going to be contributing to the median, and so that means that the mean tends to get dragged over with them. So in a case like this, the mean would be a little bit to the right of the median because of that tail. And then we can also find what the range is, for example. And we have the interquartile range that we know we can find as well. So there are all these many things that we can identify and start to use to characterize our data. Got the variance S as well, variance, which we can find. So that's all very useful. And then what we've also done, we've counterposed that to what we have in probability. So in probability, we've been plotting these things called probability distribution functions, and they look perhaps something like that. Whatever you think they will look like, that's kind of meant to be a normal distribution. This is a mathematical thing. It's defined by an equation. It's an abstract concept, whereas this is some real data that's been measured and then processed. Now these are the two things, and what we're trying to do with this course is to match these together, because this is the sort of thing we want. We want this function that actually represents this population, because if we have that, then we have a mathematical description of our population, and we can use that mathematical description to do useful things with it. So that's what we want, but this is what we've got in the middle, and so we need to make the connection between these two things. Now, first thing we should note, the area under any probability distribution function is going to be equal to 1 when you integrate over the whole possible range of x values. And that makes sense because the probability of x being somewhere over all the possible values it can be, it must be equal to 1. There's nowhere else it can be. So that's nice, and you can see we've got this point of similarity between the two. So that's why we like to plot this one this way, because then it's comparable to the probability distribution function. But what's the shape of this? Well, we don't always know, but often we can have a guess. Sometimes we can have an idea what it is based on some sort of solid theoretical point of view, and sometimes we just do it based on, well, it looks that sort of shape, so let's try that and see if it's a good fit or not to model our data. Now, in a case like this, where we were doing our materials testing problem in the first lecture, we're measuring the same thing repeatedly. So we're trying to measure one thing, we're just taking repeated measurements of it. And you remember the thing called the central limit theorem, and that tells us that if you start adding random errors many times, the distribution of the mean of samples from that will become a normal distribution. And it doesn't matter what the original error probability function was, that doesn't need to be normal, but if you start adding up those over lots of different errors, then you will get a normal distribution. And so in many instances it's reasonable to expect that you're going to get a normal distribution. So this perhaps could be a normal distribution. If you took more samples, maybe it would start to look a bit more like a symmetrical normal distribution. So then if it is a normal distribution, well, we can actually fit this curve to this data immediately, because we can calculate the mean and we can calculate the non-biased standard deviation, and then we know that, or intuitively we seem to think, well, that's going to be the best fitting normal distribution to this data. Do we actually know that yet? Not really. We're sort of told that that's what they are, but we've not proved that yet. So that's something we can look at. We're going to look at that in the next lectures. But what if this isn't a normal distribution? What if there's a reason why this is a different shape and we need to fit a different sort of distribution to it? How can we do that? So these are some questions we're going to look at in the next lectures. Is how do you go about fitting a model probability distribution function to some actual experimental data? How do you decide what the best fit is? And how do you describe how good the fit is? Also, once you've got a model like this, you can do some useful things with it. So for example, let's do our experiment. where we've been measuring the strength of this metal. Let's say we do it once and we've got some data, and this is metal from batch A, and then we do our experiment again and we take our data, and this is the data from batch B. So we've taken the data, we've got the data like that, we've fitted our normal distribution to it so that we've got a mathematical expression for both of those, and we've got that. And then you're trying to think, well, actually, are these significantly different metals, or are they probably essentially the same properties, just the different samples have slightly different means? And so that's the question that we can answer now, and we'll do that in the next lectures. You may have done that already, you may not have, but we'll look at that, how you can answer some simple questions along those lines. Another point we're going to look at is about these things, the mean and the median again, for example. So we've got the mean, we've got the median. We're not going to do anything more with that. We've got the this one here. We've got the standard deviation. What we've done so far is called point parameter estimation. So for this data, we're saying, well, this is the most likely mean for that data. This is the most likely standard distribution for that data. But of course, you know, the data has errors in it. And of course, if you take another batch of data, it will be somewhat different. And so this mean isn't the true population mean, it's an estimate of the mean of the population. And so something else we can do, rather than just saying what the value of the mean is, we can come up with a range of values, and to say that the population mean is going to be somewhere within that range of values with a certain degree of confidence. So for example, what we're going to say is that we're 95% confident that the mean is in a certain interval. And so that means that rather than saying just one value of it, we can actually give a confidence interval for what the mean is likely to be. We can do things like that to the data, which is useful for describing it. Something else we're going to do is sort of following on from this. Okay, let's say we've decided that actually these materials are different, that they are significantly different, and then we plot some data then to look at this difference. So we're going to change the variable. So let's say it's the formulation of this metal. And let's say we're changing the percentage of some ingredient in the formulation, %A. And for each formulation, we've done some different experiments, and we've calculated a value for the strength, which is what we had it in megapascals before. And we've calculated that for each data point. And so we've done a data point, perhaps that was for A, and we have the mean value. We could also plot on here the standard deviation that we find for that, and so on. Let's take a couple more values from our range of experiments, and we have points like that. Okay, so we've done that. So now it's obviously, this doesn't look like a normal distribution, it's something else. When you've got a few data points looking like this, you might think, aha, that looks like a straight line. Maybe there's a reason to believe that this is a linear relationship and that we should be able to put a straight line through there. Now I think most of you will have already encountered the least squares fitting method, where you can, or linear regression, where you probably know an equation, or you've seen an equation where you can calculate the coefficients for this. This would be an equation along the lines of tau equals A plus B A, where A is the amount of ingredient. So B is the gradient, A is the intercept. That's our value of A there. You know a method for doing that, but I think you probably don't know why that method is a good one to use. So we're going to do that in the next lectures. We're going to look at a proof for why this is, and that starts by coming up with a definition for what a most likely set of parameters would be, or for quantifying the likelihood of that they are the right parameters, and then we go about maximizing the likelihood function for that. So we can prove what our equation is for linear regression, and the reason we want to prove it is because once we know how to manipulate it, we can then change it if we need to. So, for example, what could happen? Well, perhaps we have a good reason to believe actually that this data model should pass through the origin. We know that it doesn't make any sense to pass through this value a here. It needs to pass through the origin. So actually we want to plot a different line. We simply want to have tau equals to BA. How do we find B now? If you have the equation for his, that's fine for this, but it doesn't work for that. It's not the same equation. So we want to understand the method by which we arrived at this, and then that means we can change that method to accommodate different model equations. And likewise, if you then carried on increasing the percentage of A, perhaps the data actually doesn't stay linear and it starts to level off a bit. And what we're going to need is a different function for that. And actually our model is going to need to bend over at the top, and it's going to be some sort of power law model. So again, we want to be able to know how we can fit any type of model equation the best way to the data, and we want to be confident in our understanding of why that's a good way of doing it. Okay, so this gives us sort of a picture of where we're going with the whole course, and to do this, of course, we've had to do a load of stuff. We've had to do all this sort of revision work on just making sure we know what medians are and means are, and I'm sure that's largely familiar to you, but maybe some details in there that were new. But as we've progressed, we see where we're taking it, and I think most of what's happening in the next lectures will be new to you. And along the way, we've had to learn about the sort of formal definitions of probability, the basic rules of probability, because we use those at various points along the way, and they're valuable in and of themselves to understand them. But once we're equipped with this, this will serve you well both for all your lab experiments that you've got coming up over the degree, for your research projects, for industrial placements, all of those things. Okay, so that's the first section of what I was doing. That's a recap of what we're doing on the course. Now I've got two exercises that I went through just to reinforce your understanding of a couple of useful points. And the first one is to come back to the probability distribution function to make sure that you do understand the basic characters of these, basic properties of them, and the basic ways to manipulate them and get information out of them. Now the point I was making is that the distribution that we use, it can be anything that suits our purposes, or anything that the laws of nature indicate should be used. And so we've not covered a great many different distributions. You know, we know there's the normal distribution. I mentioned log normal, binomial, Poisson. Some are discrete, some are continuous. The point is, though, what we just want to be able to do is to use them, and then it doesn't matter what distribution comes along, you know what to do with it. So this is a simple distribution that we can use for our purposes here. So we're saying we've got the probability distribution function is ax plus 0.1 over the interval of x from 2 to 10, but otherwise it's equal to 0. And of course it's important that we do define what the function is over the whole range of possible x's. Okay, so that's that. The first question then is, this is the probability distribution function. What is the cumulative distribution function, capital F? And what is this parameter A? Can that be anything we want, or actually does that have to be fixed at a particular value? Okay, so first of all, let's just think what this function looks like roughly. Okay, so this is 0 apart from between 2 and 10, and at 2 it is going to be equal to 2a plus 0.1, and at 10 it's going to be equal to 10a plus 0.1. And so our function is going to look something like that in the end. And now when we're finding the cumulative function, what we're saying is that at some point x in this direction, what is the area of that? The area of that tells us the probability that a sample is some point below x. So all the possible values below x, we integrate that, and that will tell us the probability that our sample would be below that value of x. And so to do that, we need to integrate our function. So we're going to integrate from 2, and we want to find a function in terms of x. And so we put in our function here. Now I'm going to call it a v instead of x here, just for the purposes of avoiding confusion with the integrand here, to keep that x different from that v. So that's what we need to integrate, and obviously that's a simple task for you to do. And you put your numbers in, and we will get this result: ax squared plus 0.1 x minus 2a plus 0.2. Okay, now we know as x gets bigger, this is going to give us this area here. It's going to give us the cumulative probability of our event being less than x. Obviously, when we get to this point, x equals 10, after that point the distribution goes to 0, so at this point the probability must be 1. There's no other events happening up here, so the probability must be 1 by that point. That's saying that the area of this must be equal to 1. So we can say that the cumulative probability at x equals 10 must be equal to 1, and obviously that's equal to this term here when x is 10. So a10 squared over 2 plus 0.1 times 10 minus 2a plus 0.2. And so indeed we do find out a can't be just any number we want. A is fixed because it's fixed by this equation, and if you work out what that is, we get a is equal to 0.00417 in this case. Okay, and so that all comes about because this area must be equal to 1. Now we have that, we can write what our probability distribution function is: 0.00417x plus 0.1. And if you wanted to, you could just identify what those two values are there. Okay, so that's a basic thing. Now, which is more useful? Someone asked that in the discussion forum, I think. Which is more useful, this version or this version? Well, I think the point is that if you have one, you can calculate the other. You can go either way. And so one is not more useful than the other because you can always find whichever one's more convenient. They've got some different characteristics. This version here, well, this is more directly comparable to the way that we were presenting our experimental data in the first place. It shows the details of the distribution more clearly. When you have small tails and so on, they're a bit more distinct when you look at it this way. When you plot it this way, it's particularly useful for finding quartiles. So in this case, if we looked at it, we look at the cumulative function, and this is our equation here. It's got a positive x squared term and a positive x term, so it's going to be increasing well, a greater rate than a quadratic, so it's going to look something like that. And so this is useful because if we want to find the median, well, the median is the point x which is in the middle of our data. So that means 50% of the data is to one side and 50% of the data is to the other side. So then if we're integrating this data, as we, if we were integrating the data as we were here, when you get to 50%, that point is going to be the median. And sorry, that was a mistake to shade it on that one. And so on this one, Apologies, I've made a mistake. So there we go. So this must start at 0, obviously, and it must end at 1. So that was an error. And so on this one, well, that is our x. When we get to 2, there's no data below that, and when we get to 10, all of the data is below that. So that's at value 1, that's at value 0. And so if we want to find the median, we then take the value 0.5, and that means the probability is 0.5 that the data would be above or below it, and so that would be then your median x. Likewise, you can find the quartiles very easily from this plot. Also, if we want to know the probability of an experiment being within a particular range, so if we were interested in what's the probability of data being in some range like that, well, you could integrate that area, or you can simply find those 2 points on here, and it's f of a minus f of b gives you the probability of it. So you can read off this one very easily. Okay, so those are the distributions. How do we find the mean? Found a median, how do we find the mean? So the definition of the mean is that. Why is it like that? Well, imagine if you had our list of data to begin with, like we had it here. Imagine these are all different data points, but imagine if we had some repeating data points, if we had more than one value of x1 and then we had some values of x3. When we were finding the mean, we would go, we got 3 x1s, it would be 3 times x1 plus x2 plus 2 times x3 plus x4 plus x5, and then you add them all up, divide them by the total number of them. Well, that's what we're doing here. We're taking each value of x and we're multiplying it effectively by the number of those x values. And because the total integral is equal to 1, we don't need to divide it by the total integral of this part is equal to 1, we don't need to divide it by anything, and that gives us the mean. Okay, so we can do that, and we put in our values. We only need to integrate from 2 to 10. Okay, we multiply it through. We need to integrate that. And again, obviously that's not too tricky to do. And you do that, and I got 6.18. Okay, so that's our mean that we found. If we wanted to find the median, we've illustrated it on here, but we've not found it yet. So that would be the point where f, we want to find x, where f of x is equal to 0.5. So that implies 0.5 is equal to, and then we can find our function here for that, a x squared over 2 plus 0.1x minus 2a plus 0.2. Obviously, you put in your value for a again, and when you do that, you find that our median is 6.27. Now, does that make sense? So if we look at our data here again, just get a different color. So we found our median somewhere there. Our mean is a little bit to the left of that So let's just check that that makes sense. Well, looking at this, is this symmetrical data? No, it's not. It effectively has a tail down at this end. That's where the data is sort of trailing away. And we know that that should drag the mean in that direction, and that's what we found. The mean is to the left of the median. In this case, it's smaller than the median. And that's because of this tail down here, which is tending to drag the mean down a little bit. So that makes sense. Okay, that's it. That's like a little short overview again of these distributions. And it's really handy just to be familiar with these and to be comfortable using them, because this is the sort of basic tool that we use to model real life things. Okay, the next example then was to use an example of a real experiment and talk through a real experiment and illustrate how we can use some of the techniques we've had to help us. So in particular, we're just looking at propagation of errors this time, and looking at how we can use some of the characterization we've seen just there, and how we can use the propagation of errors. And again, what we're trying to do is to come up with a picture of the data and of where the errors are, how big they are, and how that's going to affect the way that we interpret the data. And this is a real life example. Here we go. A real life from my life. So as a postdoc researcher, I used to work in UMIST, which was a precursor to University of Manchester, and I spent 3 years working on bread dough. This is a lump of bread dough, and we spent a lot of time looking at the bubbles in bread dough, and we wanted to characterize them, and we wanted to publish the work, so we wanted to have some good data to understand some new things about it. And why did we want to do it? Well, it's a long story, but in the UK we have a particular way that we make bread industrially. We have big mixers which mix a ton or 2 tons of dough in one go, and some engineers in the 1960s came up with a neat way of making bread which massively increased the speed you could make it, and it also enabled wheat flour with lower protein content to be used for the bread. And that was important in the UK because the UK environmental conditions mean that the wheat grown in the UK is not the highest protein quality, and by using this technique it meant that more homegrown wheat could be used for UK bread, and so it increased the market opportunities for UK farmers. So your traditional way of making bread, if you do it at home, is you mix the dough, you knead the dough, and the kneading starts to develop the protein structure which makes it stretchy, and it means that when the yeast produces CO2, then the bubbles can grow and it becomes a nice fluffy kind of structure. But you also let it prove, so you let the yeast grow, you let it stretch out the dough with the bubbles, and then you knock it back again, you collapse it all, knead it again, and you let that process happen again. So that's all very time consuming. And what they found is that there is a way to mix it very intensively, and it would have the same effect on the protein structure as the proving did, and so you could accelerate that process as well as using different flours. And so this meant that within 3 minutes or 3.5 minutes you could mix a couple tons of dough. It massively accelerated that process. One of the things they found was that to make that work they had to increase the amount of oxygen that was available, and so they increased the pressure of the mix. So it's a pressure mixer, and the increased pressure, obviously there's more oxygen molecules there that aid the dough chemistry. But then they also found that, well, with more air in the dough, when the pressure was released, the bubbles expanded, and that actually led to a poorer quality breadcrumb structure. So then they developed a technique where there was a high pressure part of mixing at the beginning, and then towards the end of the mix they pulled a vacuum, and that process meant there was enough oxygen, and it also meant that the dough bubble structure was then controlled in the final period to get the bubbles that were wanted for the final growth phase. So that's sort of what happens. This is a video of an industrial bread dough mixer. Here we go. And this is just to illustrate the kind of scale of the things that they're working on. That's a reasonably large one. So the operator's putting his ingredients in, and then he leaves it to it. And down comes the lid, so that seals it. And now the pressure is going to be increased, and it starts spinning the blade around to mix the ingredients, turn it into a dough, and then develop that dough. And after a few minutes, it's done. Here it comes. There you go. Ready for the next phase. It's going to get divided. It's going to get moulded, put into pans, and then it will be proved before the final bake. Okay, so that's what happens in industry, and that's really what matters, because that's where the bread's getting made. That's what we need to understand if we want to make improvements to that process or offer more flexibility and so on, the sort of research that we were doing. But obviously it's hard to experiment on something that scale. You're making a ton of dough each time. How can you run a series of experiments where you make that much dough? It wouldn't be feasible, at least not at the beginning when you're trying out lots of different ideas. So from an experimental point of view, one of the big deals that particularly chemical engineers have to deal with is changing the scale of things. So this is a miniature version of our mixer. This is the world's smallest bread mixer for that sort of process, which was made in Manchester for this process, and inside it's like a miniature version of the industrial mixer, and we call that scaling down. So there's a lot of scaling down or scaling up in chemical engineering, and first of all you have to characterize how the equipment works so that you can come up with some sensible geometry, sensible operating speed, so that what happens in here is hopefully representative of what was happening in the real mixer. And our job was to mix dough, and in particular we were interested in the bubbles in the dough. And I talked about how the bubbles get mixed in, they get broken up, and at different pressures different things happen. Sometimes the bubbles will grow once they come out of the mixer, or if you mix under a vacuum then the bubbles will shrink, which is what you wanted in the end. So we're interested in the bubbles, and the simplest way of characterizing the bubbles is just to find the total voidage of the dough. So that means that if you have some measurements, if you added up the volume of all the individual bubbles, and then you divided it by the volume of the dough piece, that would give you the voidage. It's like the fraction that is gas of the dough. Now obviously you could try and measure that by measuring each individual bubble, adding them up. We did that using X-ray tomography, but that's quite hard work and quite difficult. So there's a nice alternative technique, which is to measure the density of the dough. If you measure the density of the dough, and you know what the density of the dough is without any gas in, then you can calculate what the voidage is. How do you measure the density of something accurately? So here we are, we're talking about experimental design. Well, sometimes you can do it by finding the volume of it and measuring the mass of it. That's fine if you can do that, but finding the volume of an irregular piece of dough, or cutting away a couple centimeters cubed of dough from a blob of dough, it's soft, it's malleable, it's irregularly shaped. It's very difficult to measure the volume of that directly. So instead what you can do is you can weigh it in two different fluids, and what we have here is a balance, and the balance has a little table sat on top of it. That table is sitting on the balance frame here, rather than on the pan itself, which is being weighed. So this part isn't being weighed, and we've got a water bath to have a controlled temperature, and then here we've got some liquid. It's xylene, as it happens, and we have some liquid at a controlled temperature. And then this wire frame, which you can see here, that slots underneath the little support, and that's what's connected to the pan of the balance. And so what we're weighing is this wire frame, and then we have two cups. We can put a sample of dough on the top, we can weigh the dough in air, and then we pop it in the bottom in the liquid, and we weigh the same dough sample in the liquid. Obviously the forces on that dough piece are different. When it's in the air, well, there's the buoyancy of the air effect, but that's very little. So essentially we're just measuring weight that can be effectively related to its mass, via G. Whereas here you're measuring its weight in a different fluid, and here there is a significant buoyancy force, and the buoyancy force is equal to or related to the density of the liquid and the volume of the dough. And so because we've got the volume of the dough in that characteristic, that means that we can use those two weights and find the density of the dough piece. But we do need to know the density of the xylene liquid to do that, but that's easier to find. And so the objective is we did some experiments at different pressures, and we found the density of the dough once it had come out of the mixer, and then using the density of the dough and the value for the gas-free dough density, that's a piece of dough that had no bubbles in, we could then find out what the voidage of the dough is. Okay, and look at how that changes with some process conditions. You know, none of that you're very interested in, obviously, but this is just to give you an example of a real experiment and some of the things that come up along the way. We're just going to focus in at the moment on one part of it, which is to find out what these density values are. We're not going to worry about the change in pressure. We're just going to take one of these data points and we're going to study how did we get that and how can we consider the errors that happened along the way. Okay, so the starting point for that is to have an equation. This equation tells us what the density of our dough piece is in terms of the different things we've measured. We've got the density of the xylene, we're expressing it as mass, so the mass of the dough piece when it's in air and the mass of the dough piece when it's weighed in xylene. And this is an equation, so this equation is coming from the physical nature of the system. This accounts for buoyancy effects, so this is from physics. So if we have an equation, we can then do some experimental design and we can run some experiments to get data. So we're just going to look at the top run here. So what have we got? We've got the mass in air and we've got the mass in xylene. And we've repeated this, so we've got it once, twice, 6 times. So we've done an experiment, we've repeated it 6 times. So we've got some different samples. Now for each of these occasions, we can calculate what the density is. And for each of those, we need to assess what the accuracy is and what the error propagation in that is. Okay, so these give us the masses. And then for the value for the xylene, we did some different experiments looking at how the density of xylene changed at different temperatures so that we could read a value off here. And we'll come back to that, I think, maybe in a later problem session. So the main thing we're looking at is the mass measurement, and again, you can check your scale. We talked about this before. So let's assume that the balance was perfectly calibrated, but it still has some linearity error, so it's plus or minus 0.0002 grams. So even if we'd had it just nicely calibrated, there's still likely to be some error up to that. Now, of course, you've seen everything we've talked about with regard to errors and error propagation and so on. It's assumed that our errors are normally distributed. And most of the theory that we deal with makes the assumption that we have normal distributions, and that enables us to make nice predictions and nice characterization of what happens. In real life, obviously, we don't know that. When we have a measurement on the balance, we don't know what the standard deviation of that measurement is necessarily. We might not be taking enough repeats to find that and so on. But what we can do is we can take this as an indicative value. We can use the theory that we have based on this value. And I suppose this gives us a worst case scenario. This is the worst value for what the linearity is, but hopefully it actually will be a bit better than that most of the time. So we can take that value and use it as an indicative value. In this case, it would be a worst case scenario. Okay, so this is what we're talking about. We've now got an error for both the mass in air and the mass in xylene. They've both got the same error, 2 times 10 to the minus 4 grams. And the error of the xylene density, rho x, we're going to take as this value, 1.73 times 10 to the minus 4 grams per centimetre cubed. And that's just a value that I've calculated separately based on the xylene density measurements. Okay, so what we want to do next is to see how to propagate our errors. There we go. To get an estimate for what the error in our density is going to be. So we're just going to do that, and that will give us a bit of practice doing the error propagation analysis that we've talked about before. Okay, so the starting point is to have our equation, so the density is what we're trying to find, and we've said that's equal to the density of the xylene, mass in air, divided by mass in air minus mass in xylene. So that's our equation, and each of these three terms has some uncertainty associated with it. So what we want to do is to calculate what's the uncertainty going to be in the density given those things. And we know that we have the general equation for the propagation of the errors, and it's the sum of the partial derivative of our function with respect to each of its variables multiplied by the uncertainty associated with each of those variables squared. Called them xi just because these have got different symbols, so xi just represents all the different variables. So we need to find what these partial derivatives are. So d rho by d rho x, so differentiated by that, and then we have ma divided by ma minus mx, d rho by d ma that's going to be equal to rho x. How should we do that? I could say u over v, so it's v du. So that's v du is 1 minus u dv. That's ma, differentiate that, is equal to 1, so it's minus ma over v squared. And that can be simplified a bit. We've got that ma minus ma, so it's rho minus rho x mx over ma minus mx squared. So that's the term for that one. And then the third one is d rho by d mx, and then that comes out at rho x ma over ma minus mx squared. Probably got minus it. And there we go, so we've got those ones. And then we've got these individual error terms. So we can find what these are now for each of our pairs of values of ma and mx, and we know what rho x is. For each of those situations we can find it, we can square it, we can multiply it by the uncertainty of the parameter there, and we can then add them up. So we've got three parameters, so there are going to be three terms in this summation, and each term in the summation is associated with a different parameter. It's the way that the error associated with that parameter gets propagated. So we can calculate it, obviously we can just calculate it as a whole, but we can also calculate it parameter by parameter, and then we can see which ones are actually causing the biggest errors to get propagated. So that's what I've done here. We've got the contributions to the propagated sigma squared. There's the one from the xylene density measurement, there's the one from the mass of the sample in xylene, and there's the one from the mass of the sample in air. And you can see they're quite different actually. This one is the largest at 5 times 10 to the minus 8. This one is the smallest at 1.6 times 10 to the minus 10. Obviously we then add those up and then take the square root, and this gives us the propagated error. Okay, so what we can see is that we've now got a volume propagated error. Fantastic, that's what we wanted. That's very valuable. But actually you can see that most of it's coming from one source here. This is the sum of the 3 data points, 5.67 times 10 to the minus 8. It's only slightly larger than this one here, 5.4 times 10 to the minus 8. So what we see is that the xylene density uncertainty is dominating the overall uncertainty. And that's often the case because we've got the squared terms in all the data here. that tends to accentuate differences between the errors. So if one error is larger than another, then it tends to be the case that once you've squared it, added them up and taken the square root, it's the larger errors which dominate the overall characteristics. So that's useful to know, because it means that if you're doing error analysis, or if you're looking at your experiment thinking how can I minimize the errors, really your time is best spent focusing on the biggest errors and trying to get those down, rather than worrying about identifying all of the different small errors. It also means that if you're doing error propagation calculations, if you're confident that some errors are going to be small and negligible, it means, again, you don't need to necessarily include all of those into making it complicated, long-winded calculations. The important bit is to track the largest errors as they get propagated through the calculations. Okay, so that's an example of error propagation in a real context. But then the final thing is to check actually what your assumptions are, because here we've assumed that everything else is perfect about our experiment. We identified 3 possible sources of errors, so 3 measurement errors. But actually, is there anything else in the experiment that is uncontrolled and has random effects, which is dominating the errors more than that? And so remember, we did 6 experiments, and that's why we do multiple experiments, is because we're not actually sure that any one of those is perfectly controlled. So when you do 6 experiments, you can then calculate 6 densities using our equation, and then when you have 6 densities, you can find the average, the mean density, and you can also look at the standard deviation of those 6 that we found. And then we can compare that standard deviation to the propagated error. And so this propagated error, it's an estimate of what the standard deviation might be. Obviously they're somewhat different things, but when you look at them you can see they are significantly different. This is about 3 times 10 to the minus 3, and this is 2 times 10 to the minus 4. So we have an order of magnitude between them in difference, and this is the one that is larger. So even though we've gone to the trouble of looking at our error propagation based on our best estimates of how accurate the individual measurements are, we actually see that from one experiment to another the amount of variation is significantly more than this. And what does that mean? Well, it means that from the point of view of understanding the process and the population of all the possible values that we could be getting for a given experiment, this doesn't really represent the variation that we're seeing, because it's so much smaller than this. So it means that in terms of what we do, spending time on error propagation is less useful. It means that spending time on improving the measurements of those particular things we've measured is less useful, because that's not where the errors are coming from. What we would need to do is spend more time trying to minimize the variation from one experiment to another. These are completely independent runs where we've started again, we've made a new batch of flour, we've weighed it out again, we've put it into the mixer again, repeated the whole experiment, and that's what the variation is. Obviously the samples get taken from different parts of the dough. There's going to be a distribution of voidage throughout the dough. So all of those different factors come into play here. So it's the experimental design which is giving rise to the uncertainty rather than the individual measurements. So whenever you're doing an experiment, it's really important to assess that, and there's no point focusing on the accuracy of your measurements if actually there are uncontrolled variables in your experiments which are giving rise to bigger differences overall. And for most engineering experiments, it's probably the case that that's going to be how it goes. Engineering experiments typically aren't that well controlled, as opposed to like a physics experiment or a chemistry experiment, because we're dealing with real processes, and the real processes are complicated. They can't be simplified too much, because then they stop being representative of what actually happens in the industrial process we're concerned with. Okay, so that's the point of that, is to make that comparison. So thank you for visiting and for listening. I'm going to put up the next week's lectures shortly. Then you can look at the final topics for the module, and hopefully you'll see how this sort of rounds off the whole package. Thank you very much.